spring, block, and an incline. Now we have a spring, block, and an incline. This time we're going to compress the spring, then let go of the block, and it'll shoot it up the incline here. We'll be looking for various things. We have a spring constant. We have a distance that the spring is compressed, centimeters. We're going to have to convert that to meters. And we have a mass of the block. What is the initial energy of the block? Find the initial velocity of the block when it leaves the spring. And what vertical height on the incline does the block reach before it stops and slides down? What is the initial energy of the block? The spring is at the lowest level in the problem, so we'll assume the GPE is 0. We can set that. We're totally free to do that. When the spring is fully compressed, its initial energy is just elastic potential energy. The box is not moving, so there's no KE. So the initial energy is all EPE, which is 1/2 kx squared. Plug in our numbers, and be careful over here, convert centimeters to meters for the compression of the spring. We use unit conversion here, where 1 meter is 100 centimeters, just like 1 year is 100 years. And we get 0.064 meters. And our initial EPE, and actually that will be the energy at any point in this little traveling block, is 0.115 joules. We want to find the initial velocity of the block when it leaves the spring. The GPE is still 0, but all of the spring's EPE is gone. It's all transformed into KE. The spring has sprung. It's at a relaxing point now. So we set our initial energy, which is EPE, 1/2 kx squared, is equal to 1/2 mv squared. We could also set this equal to the energy we found in the previous slide, but I like working with letters, and only at the very end do we solve for the numbers. Our EPE is 1/2 kx squared, and our KE is 1/2 mv squared. First thing we do, multiply both sides by 2. We get kx squared is mv squared. We're interested in v, so we're going to switch the order of the equation, set mv squared as kx squared, divide through both sides by m, and then take the square root of both sides. So we're almost done. You could actually solve this right here, put the numbers in there, but whenever I have a square under a square root, I like to take it out. Take the square root of x squared and get x. This way, if you leave it in here, you have to square it, and then you're taking the square root again. Here, I took the square root of a variable, which is a lot easier to do than take the square root of a number. So I have velocity is the square root of k over m times x, put in my values, and I find I have a velocity of 1.24 meters per second. What vertical height on the incline does the block reach before it stops and slides down? So there's a key. So what's going to be its kinetic energy at the top? 0. The maximum height is when the velocity is 0. It stops. And we have our little speed lines going up. Then at the top it stops, and we're going to find that value of h. The only energy it has is GPE. When we get to the trig physics course, we'll actually find the distance that it goes up the incline. But for now, we just want to find its vertical height above the ground. Set the initial EPE, again, algebraically, equal to the final GPE of the block. We actually don't care about the velocity of the block, don't need it, just need initial and final states. We have 1/2 kx squared is mgh. We want to find height, so we switch the equation around. So we have mgh is 1/2 kx squared. And we're going to take a little shortcut here. Instead of dividing through one variable at a time, we'll divide both sides by mg. mg gets canceled, and I have h is 1/2 kx squared over mg. I now put in all my numbers, and I find the height. This height here, the vertical height, is 0.0780 meters, or 7.8 centimeters. We continually talk about physics problems and how it's always best to algebraically solve them first before substituting in numbers. That also applies to conservation of energy equations. It's best not to solve numerically for the total energy and set that equal to the energy equations for where the box or object may be. Well, of course, they'll ask you for the total energy, and that's great, solve for it, but then put it aside. Set the energy equations at the various points of the motion equal, solve that algebraically, and then put in the numbers. You might be able to cancel out things like a half when setting EPE equal to KE, or variables like m when setting GPE equal to KE. That actually gives you a better understanding of the problem too, because it shows that when an object is on an incline or a height and slides down, the velocity it has at the bottom does not depend on the mass. That's a good physics point, which you may not have gotten if you just put the numbers in ahead of time. And also it makes the math somewhat easier and reduces the chance for calculation error.